announcements for this week. So in lab this week, we will be starting experiment 6, or we will be doing experiment 6. On your syllabus, it also says experiment 5, which is information about the technique you're going to learn. You're going to learn how to use IR spectroscopy this week. You'll have your quiz. Next week, experiment 3 report is due, so hopefully everybody's getting their notebooks back from their laptops this week. Next week, experiment 3 report is due, even though it's fall break week, the report is due, so we'll talk to you about that in lab this week. And then next week, for open lab, since it is fall break, we won't have open lab Monday or Tuesday because classes aren't in session. So we'll have open lab Wednesday, 9:30 a.m. to 3:30 p.m. like normal. Thursday we'll have open lab because we're not going to have lab Thursday if we don't have lab on Tuesday. Okay, so we'll have open lab from 9 a.m. to 5 p.m. and then Friday from 10:11 from 9:30 a.m. to 3:30 p.m. like normal. Because we don't have lab next week, we won't have a pre-lab lecture. So the next time I see you will be 2 weeks from today for pre-lab lecture. All right? So go to workshop because you have an exam next week. So instead of coming here, go get ready for the exam. And then in 2 weeks, when I see you again, we're going to start experiment 7, part 1. It's a 2-week experiment, but you need to make sure you have the pre-lab for both parts that week, okay? So you need to have the complete pre-lab ready to go in your lab notebook, all right? I'll talk about this yellow sheet that was in the back here in a little bit, but this is what you should pick up. If you haven't picked it up on your way in, make sure you pick it up on your way out. I also have it posted on Moodle for the Chem 255-11 section, okay? So you'll need that this week for figuring out your IR spectroscopy. All right, so a lot of things to cover. I got to cover experiment 6 and I've got to cover IR today, so we'll get going here. So for experiment 6, you're going to use multiple techniques, so it's going to be a little bit different than experiment 1 with our unknown here. We're going to use multiple techniques to identify an unknown, okay? And this unknown is composed of one thing, not multiple things like experiment 1, okay? And the unknowns have specific functional groups that are involved. So it could either be an alkene, an alkyl halide, an alcohol, a ketone, or if there's nothing else besides carbon and hydrogen and it's not an alkene, then it's just purely an alkane. So those are our possibilities for unknowns this week, okay? And these don't necessarily have to be straight chain, right? They could be rings, things like that, okay? But these are the functional groups that you are looking for this week. So we're going to use many techniques to figure out what your unknown is. So one of the first ones is, depending on if it's a liquid or a solid, we will be collecting a melting point or a boiling point. So the new piece of equipment that, besides learning how to use IRs, that you're going to be introduced to this week, is in your drawer is a piece of glassware that is this piece of glassware without the test tube on it, but this piece of glassware with the side arm on it. We're going to use that this week for the liquid unknowns to distill the unknowns, but also to purify them, okay? So, to collect the boiling point of them by distillation and to purify them, okay? So all of this is all connected in one, and then we will put our sidearm test tube on it to collect your unknown as it distills. So basically we've got our distillation pot. This is our riser or kind of three-way adapter where the thermometer comes in. Here's where it condenses in the arm, and then it goes down into whatever you have on the side to collect there, either a test tube or a sidearm test tube. Couple things to be careful of. First of all, you're going to clamp it. You want to make sure you have a stir bar in here when you start heating it. You all have different unknowns, so you're going to, instead of using a hot water bath, you're going to use your heating mantles again for heating the unknowns and distilling them. Okay? So we can't tell you exactly what temperature to distill at, so you're going to have to be kind of vigilant if you have a liquid as far as figuring out how much heat you need to give it in order to get it distilled. So you got to keep, if you add heat and after a few minutes don't really see any response, then you need to keep adding heat, okay? So you have to keep turning up the dial on your ohmite. Your thermometer, you're going to use the regular thermometer you've used before, but you're going to have the stopper adapter, so we'll show you that. Make sure that thermometer tip ends up underneath this arm so that you're getting a good reading, because this is how you'll determine the boiling point. So you need to make sure you're getting a good boiling point temperature for the reading, okay? And then as it condenses over, if you're using the sidearm test tube, make sure it's pointed up, not down. Otherwise, your unknown will drip out as it comes over, okay? So make sure you don't lose your unknown as it's being distilled. When you add unknown to this, make sure you use your stemmed funnel so it goes past this arm, or you may have to tilt it to the side a little bit so it doesn't all run out the arm when you're trying to put it in there as well, okay? And some of these unknowns are really, some of the liquid unknowns are really volatile, some of them are not. And so you want to make sure that after you've distilled it, you keep your unknown in a secure place where it's covered and not going to evaporate on you. Because if you run out of unknown before you get all the tests completed, that'll cost you 5 points as far as your report is concerned if you have to get new unknown. Okay, so you have to be really careful with it, not to lose it. All right, so we'll show you that setup in lab this week. Okay. So then another test that we're going to do is we've got to figure out if you have a halogen or not to determine if you have an alkyl halide or not. And so what we're using is what's called the Stein flame test. And so you're using a copper wire, so different than what you used in Gen Chem when you were trying to figure out the metals present with the flame test. This time you're using copper wire, and you're going to put a little bit of your unknown on the copper wire, and then if you have an alkyl halide or you have any halogen, then you will get a green flame as a result. So that is what you're looking for, okay, is the green flame will tell you that you have a halogen. And that's going to be the only way you know the difference between the alkyl halide or the alkane. So you want to make sure you get a really good flame test. Make sure your results are reliable, okay? And so we'll show you how to do that in lab this week as well. Next thing is we're going to figure out what our unknowns are soluble in or not. And to do this, you're going to use test tubes, and then you want to use 1 milliliter of solvent and 3 drops of your unknown. You don't want to use any more than that, because otherwise we're just making unneeded waste, okay? And in your lab manual is a table for the solubility test. You want to follow that table, okay? So you want to do these tests in order of the table, starting with water. And you're going to follow along depending on the trend you get and determine what functional group potentially is present, or functional groups. But you also want to follow this table. So for example, if you find that you have something soluble in water and not soluble in ether, you are not going to keep going, okay? Yeah?
You say 3 drops of unknown, so what does that look like for a solid?
You'll just use like a few crystals of your solid. So just enough to be able to see it. And a lot of times solids are actually a little bit easier to see than liquids because you're looking at liquids and liquids together. So with the table, you want to make sure, follow the pattern. If it tells you don't do the rest of the test, then don't do the rest of the test, okay? So depending on what pattern you get for solubility, that will determine what other tests you're going to keep doing. But make sure that you follow what is in this table, okay? And like I said, this guy is in your lab manual, all right? So the five things you're testing are water, which you can just use a little bit of RO water, diethyl ethers in the red cans, 1 molar HCl, 2 molar NaOH. Those are both in bottles. You used them last week in the hood. And then the concentrated sulfuric acid is the last one. Be careful with this. It's concentrated sulfuric acid. You don't want it on you, okay? So I would recommend wearing gloves with this and not get it on you. And if you drip any, we need to get it cleaned up right away, okay? So that someone else doesn't get it on them. Also with the unknowns, I recommend wearing gloves anyway, just because you don't know what chemicals you're working with because they're unknown, okay? Now with that, with gloves, you have to be careful. Don't write in your notebook with them on. Don't handle your lab manual. Don't handle your cell phone. Don't turn door handles. Don't use the computer of the IRs with them. So with the gloves, you got to keep in mind you have gloves on. When and where can you touch things with the gloves on, and when can't you? Because then you're going to have chemicals on the gloves themselves. The next one is then interpretation of your IR spectrum. So I'll get back to this once I talk about using IR spectrum. And IR spectroscopy. So we'll get back to this guy, okay? Actually, a couple things I'm going to show you though. Here, I'll list them on here. Eventually, you will need to look up known spectra to match your unknown with something that is known. So databases that are good for that are SDBS, which I'm going to show you here in a second. Get this guy on. Aldrich Spectral Viewer. And then if you're not finding information that way, you can use NIST website, which is http://webbook, so 2 B's, .NIST, my IR stuff is already up here, .gov, and then / chemistry. So the first one I'm going to show you is SDBS. If you just Google SDBS, just pick, it's a long web address, so it's just easier, actually they've shortened it a little bit, but just Google SDBS and then pick that top selection. And then it will go to this database. So you've got to get down on the bottom, say I agree to use it under their terms that they've specified. And then you will either put in the compound name you're looking for, you can put in molecular formula, molecular weight, CAS registration number, all sorts of different criteria for looking for the different compounds. You most likely will put in a compound name. So if we, for example, type in 1-bromoethane, and then hit enter. Whoops. Doesn't want that one. Let me go back. Well, that's really funny. It worked earlier. We'll try ethyl bromide. See if that comes up. There we go. Oh, there's bromoethane. But this one is coming up with different choices than my computer here. Well, here for ethyl bromide, we'll click. We're interested in the IR. Eventually, you could look up known NMR spectra too, which we'll use next semester. But we click on IR. What we want to make sure is it says liquid film or neat film here. You don't want anything that says vapor phase because it does not have the same intermolecular forces that something in the liquid phase or neat phase has if it's gas, if it's vapor phase. And when we'll talk about IR spectroscopy, what's involved with IR spectroscopy is going to change depending on what intermolecular forces are in action, okay? So you look up your spectrum, and then here's the possibility of the spectrum, and then you're going to try and match your IR spectrum with this one and see if it matches or not, okay? And then eventually what you want to do is print out this part is the part you would print out, all right? The other database that you could use is Aldrich Spectral Viewer. It is not it's not a web-based one. It's a program on the campus computer. So you'll have to use a campus like computer lab, something like that. So it's on basically the general campus clone computer labs. The way you look up things is you click on this question mark here. You type in what you're looking for. I'm going to try 1-bromopropane on this one instead. And then hit execute. Oh, it doesn't want to find that for me. Let me try this. There we go. We'll go with 2-bromopropane because that one is available. All my searches are striking out here. So then you want to click on the one you want, or have the arrow there. Hit click hide result, and it defaults to come up with NMR spectra. So you want to look up here, and if these tabs are available, then that means the IR spectrum is available. So we'll look at the IR spectrum, and it says that it's neat, so we can use that as a possibility. And then we want to know what these, what the peaks, what their wave numbers are. And so the way that you do that is you can click on this icon, and down here is where you will, the middle guy, you'll set the threshold, and you just, whoops, go back. You move the threshold up and down, and whatever's below it will get marked. So you just left mouse click, and then whatever below it's going to get marked. And then if you decide this is your thing that you're looking for, you'll click on print. Make sure that print peaks on spectrum is selected, and then we would say okay to print it, okay? And then the NIST website, you just go to that website and look up information. The only thing with that one, when you find IR spectra, they don't have the peaks marked. So it's just, it will have potentially spectra on there, but I would try STBS or Aldrich Spectral Viewer first, because both of those have places where the peaks are marked, okay? All right, the next piece of information is our chemical characterization test. And we have 4 of those. We've got bromine in carbon tet. We've got potassium permanganate. We've got 2,4-DNP. And we've got what we call CAN, our ferric ammonium nitrate. So there's our 4 possibilities. So I'm going to go through each of those right now. So the bromine test, it reacts with alkenes, okay? And so the alkene, whether dissolved in a solvent or, because you use dichloromethane as the solvent here, so whether it's a liquid or a solid, it's dissolved in the solvent, you're going to have some sort of colorless solution, okay? The bromine is kind of a red-brown color, okay? And what happens is when you add this red-brown color to this colorless alkene, it turns colorless, okay? So it looks like it's kind of the opposite of what you expect for the reaction. You're going from colorless, add red-brown, and goes colorless again. So if it goes colorless, that's actually a positive test, okay? If it stays red-brown, then it's not reacting. So what happens is the bromine reacts with the double bond and reacts across it. And once you talk about bromination of alkenes, you'll understand why it adds across this way. And if it reacts with it, then it's forming a colorless solution, okay? And what will happen is if you have an alkene, you can add many drops of the bromine and keep adding it, and it'll keep turning colorless, all right? So once you get to like 20, 25 drops, I'd call yourself done with the test. You don't have to keep adding it till that red-brown color persists. The lab manual tells you to keep adding and counting how many drops until it persists, but some of these, like, it could, you know, you're just wasting bromine at that point, okay? So you get to 20, 25 drops, you can call it good. That's probably a positive result, all right? Now bromine also, so that's our electrophilic addition. It can also do a substitution reaction. So if we have an alkane, we add bromine to it, and we add heat or light, then we get this substitution. So you substitute for the proton, you're substituting a bromine, okay? So you brominate this alkane. The other thing that you give off is HBr gas. All right? And so it tells you when you do the bromine test to also make sure you're testing the pH as the reaction is occurring. This is why, because if it's an alkane, then you'll get reddish color on your pH paper, meaning that you probably have generated HBr instead of it reacting with an alkene, okay? So this is a false positive test because you're not looking for this result, you're looking for it reacting with the alkene, all right? Now, when you get to determining what's going on with this test, don't use the pH paper alone to determine what is going on. The bromine test and the potassium permanganate test have to be used together. They both test for alkenes, okay? And you need both of them to be positive for you to have an alkene, all right? So if you get a positive bromine but a negative alkene, or sorry, a negative permanganate, most likely it's reacting with an alkane, it's not reacting with an alkene, so you'll probably see that pH paper. But if you get a positive bromine and a positive permanganate, most likely it's because it's reacting with the alkene. So you could still see a little bit of acidic pH paper even though it is reacting. So don't use the pH paper as your end-all determinant, all right? So with the potassium permanganate reaction, again, we would have our alkene either liquid or solid dissolved in acetone. It's colorless. We add potassium permanganate. It's really dark purple. Then it reacts and it reacts across the double bond, forms this diol, okay? That's also colorless. but it also makes manganese dioxide, and that's what you see as evidence of the reaction occurring, okay? So it's this byproduct of the manganese dioxide is what you're looking for, right? What you will see is, as you may not see that much of that solid right away, but that color starts fading and turning a different color. That's most likely it reacting with the alkene and starting to work towards the manganese dioxide forming. Give this one, the bromine test is really instantaneous. Give the potassium permanganate one like 2 to 5 minutes because it takes a little bit longer for it to react, okay? But you need both of those to be positive to have an alkene. For the Dnp test, this is reacting with ketones or aldehydes. We only have a ketone possibility for this unknown, okay? So we're looking for it to react with ketones. You've got a ketone, the 2,4-DNP is 2,4-dinitrophenylhydrazine, so it's this species here, in sulfuric acid and ethanol, okay? So be careful with this one, it was made in concentrated sulfuric acid. Also, you get any of this on you, it turns you orange really quickly, so wear gloves with this one. These guys, make sure you wear gloves with them because you don't want the bromine or the permanganate on you, okay? Same with here, you don't want this on you. When it reacts with a ketone, then what we make is 2,4-dinitrophenylhydrazone is then what this species is. So you start with your ketone dissolved in ethanol. This is kind of orange-yellow solution. If you get a positive test, you're going to get a yellow to orange solid that forms. Now be careful because what is acetone? What functional group does acetone have on it? It's a ketone, right? So don't contaminate your test with acetone because if you get acetone in here, you're going to get a false positive, all right? Because it will react with the 2,4-DNP. Same with here, be careful not to get acetone in here, but because either of these can also react with acetone. So keep acetone out of the equation. Make sure you don't have anything contaminated with acetone when you're trying to do these tests, okay? All right, the last test is kind of not really, it's not really a reaction that we can easily show you. It's more a complexation is what happens. And so for the alcohols, you're reacting with ferric ammonium nitrate with an alcohol. So we've got our alcohol here, plus here is our ferric ammonium nitrate. So here's our nitrate. And the counter, that where the ammonium comes from is you've got 2 ammonia that are your counter ion here, okay? So this exists as the ferric and the nitrate together, counter ion is your ammonium, okay? So you'd have 2 of those, which would be your, actually, not show it like that. You've got 2 of those hanging out there with your ammonia, all right? Okay, so here's our counter ions. They don't participate at all, okay? So we start, this is a yellow solution, okay? Maybe a little yellow orangey solution. When you react it with an alcohol, then you get this complexation of the R group from the alcohol, here's the oxygen from the alcohol, and it reacts with this part of our ferric ammonium nitrate, and we get this. This complex then becomes red. There's not a precipitate that's formed, it just turns colors, okay? And so what you're looking for is that red complex, and then it also gives off proton and nitrate in the process, okay? So this is our complex that you're looking for. And as far as like a true reaction, because this is a more organic metallic reaction, we're not holding you responsible for this guy, but this is the complexation that takes place, okay? So you're looking for a yellow to red complex for the alcohol. So those are our 4 chemical tests, okay? Then the last piece of our, here, I'll put it down here. Our last piece of our methods for figuring out what we've got is to do a literature search for the unknown, okay? And 2 pieces that you need to do this is the melting point or boiling point, and you need the functional group or chemical class of your unknown. Okay. So in the back of your lab manual is a couple appendices. The first section is a bunch of tables of compounds and melting points and boiling points, okay? This is what you're going to use to help you figure out if you've got what your unknown is or not, okay? And so you want to find the table for the chemical class. So you need to know, do you have an alcohol, do you have a ketone, alkene, alkyl halide, alkane, okay? Find that set of tables. Then you need your melting point or your boiling point, and you want to look in the range of plus or minus 10 degrees of that melting point or boiling point. Look at the possibilities for an unknown, and then you're going to look up the IR spectra of these unknowns, match your IR spectrum with one of these, and then you'll have what your unknown is, okay? Yeah?
So this is a topic, but for the prelab, are we doing 1 for 5 and 1 for 6?
I'll talk about the prelab here in just a second. Yeah. So just make sure when you go to look at this information, you need melting point and boiling point. You need to know the chemical class, and your chemical characterization test and your IR spectrum should go together. Okay. Solubility test should also help with that, but chemical characterization test or the flame test and the IR spectrum should go together. All right, everyone good with this? Okay, and just remember, don't look for just the exact melting point or boiling point. Go plus or minus 10 degrees. Okay, so you're going to have a 20-degree range that you're looking over for possibilities. Okay. All right. I'm going to get to this guy in a second because here's our flow chart. Okay. So we're low on erasers today here. So for prelab, so your prelab is for experiment 6, okay? So first of all, you need your purpose. You'll need the chemical test reactions. So we just went through all those, and they are in your lab manual. You'll need your physical data table, okay? Is what you need in there is the chemicals for solubility tests and the chemical tests. Okay, that is what's going in your physical data table. So there's not a list of unknowns that you're going to put in there. It's the chemicals that would be used for solubility and chemical tests, and that information. Then, flow chart. Here is your flow chart. Your flow chart is in your lab manual, so it's a little bit different than your normal flow chart. It's just showing you get your unknown, what are the steps basically to identifying your unknown. Okay, so here is your flow chart, and again, it's in your lab manual. Okay. Number 5 is your any new equipment. You guys have that small scale simple distillation apparatus. That is your piece of equipment to draw here, all right? And then 6 are your references for finding your data for the prelab, okay? So there's no yield this week to show, okay? No yield calculation, all right? References should include lab manual and then whatever references you needed for your physical data table. Yeah.
Just double checking for the flow chart, is that what is appearing up there?
Yes.
Okay. Great.
Yep.
Thank you.
Yeah, and that is in your lab manual.
Yes.
Okay. So that flow chart is what you're using. Yeah.
So you say for the references, we have to like write down the interpretation of IR spectroscopy references, or just lab manual?
Just so your lab manual, and then what you use to put your physical data table together. Because wherever all that information comes from, you've got to put in there. Yeah.
Was all of that also be in the lab manual, or should we look online?
No, you're going to have to look this information up. Yeah. Okay? All right. I'm going to get back to experiment 6 here in a minute, but I'm going to explain IR, and then we'll talk about experiment a little bit more with experiment 6, okay? In terms of IR spectroscopy. All right. So if you guys remember the electromagnetic spectrum from Gen Chem, okay? It's, huge, big spectrum. The visible area is just this tiny little sliver in here, okay? One side is the ultraviolet side, the other side is the infrared side, okay? Which was the high energy side? Ultraviolet's high energy, right? Infrared was not, right? Okay? So the infrared spectrum, you're not high energy, okay? So when we're looking at IR spectroscopy, which is infrared spectrum, we're not looking at the high energy side. So the types of things we're going to be looking for are things like bending and stretching of bonds. We're looking at what happens to the bonds in the molecules as you apply energy to it. What does it make it do? Okay? And so these are different types of stretching and bending that can happen in that molecule. Some of it's symmetric, some of it is asymmetric, and it depends on the type of bond that is there and what type of atoms do you have. Do you have really small atoms? Do you have a small and large atom? Where this occurs in the IR spectrum depends on what you have there, okay? All right, get rid of this guy now. That's the end of show and tell with the Okay, so we've got our lower energy part of the spectrum, so we're not doing things like electron excitation, things like that happen in the UV. We're talking the lower end, okay? So here's kind of general information for a spectrum that we are looking at, okay? So the regions of the IR spectrum, this is also in your textbook in McMurray, okay? We go from 4,000 down to about 600, 650, and the units we use is inverse centimeters, okay? So 1 over wavelength, inverse centimeters is what we report this in. And we call those wave numbers, all right? So over here in the 4,000 area, we're looking at NH, CH bonds and the stretches that are associated with that. Then we're looking at carbon-carbon triple bonds or carbon-nitrogen triple bonds. Then carbon-oxygen, carbon-nitrogen, or carbon-carbon double bonds. And then we get down towards the fingerprint region, and I'll show you in a minute what is meant by the fingerprint region. As far as making identification, you're basically going to be responsible for this area, which is what is on that yellow sheet. That's why we handed that out, okay? So basically, what you're responsible for is about 4,000 to about the low, just about 1,400. The CH bending goes down about into the 1360s. Okay, so down through the CH bending is what you're responsible for. And so that's basically what that yellow sheet is. So here's just example of what an IR spectrum looks like. Depending on what is in the compound, you will see different peaks corresponding to different wave numbers. So this is just ethanol. Okay, so it's got OH in there. We've got a big OH stretch. We've got some CH stretching, and then we've got other information as we go across. Okay. And like I said, this corresponds to the table that I just gave you. Okay, so you've got this table. Yep.
When you say peaks, are they like inverse peaks?
They drop down, so they're peaks that drop down. Okay. And you refer to them as peaks. That's what they are. Okay. So the units are wave numbers or inverse centimeters, and they are peaks is what you're talking about. Okay. So this is the table you just got. The other table that you have available to you is in your textbook. The difference between the two, the yellow sheet gives kind of more general, broad regions for each of the functional groups. There's more specifics on the table 12.1 that's in your textbook. Okay, so you've got two resources for you: textbook and this. All right. Okay, I'm going to just show you so you guys can see examples of different spectra. What you're looking for when you're trying to characterize this information in terms of experiment 6. Okay, so you're looking again between 4,000 and almost 1350 basically. What type of peaks do you see? So we have cycloheptene here. It has a double bond, so we're going to see the sp2CH stretch. We're also going to see the sp3CH stretch, and we're going to see the C double bond C stretch around 1600. Those are the important things, and then we've got some CH bending here as well that we would identify. All right. So those are the type of things that you're going to look for. So let's go through with another one here. Here's an alcohol, 2-butanol, okay? We've got an OH stretch, we've got an sp3CH stretch, and then we've got our CH bending down here. So with the alcohols, you're going to see most of the information here with then your CH bending down there, all right? And when you label your spectra, when you get your spectra, you want to write on there CH, sp3CH bending, OH stretch, or sorry, sp3CH stretch, OH stretch, CH bending. You want to label the peaks like I've done here, okay? So here's a ketone. We've got sp3CH stretching with the ketone, and then we also have the carbonyl. The carbonyl and the C double bond C sometimes get confused with each other, but the carbonyl is usually late 1600s to the 1700s. The C double bond C is going to be the early 1600s or late 1500s. Okay, so that's how you can tell the two apart. Here's the bromopropane that we looked at earlier, except for this is one bromopropane. There, besides the sp3CH stretch in the alkanes, there really isn't anything else to see there, okay? So you're not going to see anything else in this area except for your CH bending. But you won't see an OH stretch, you're not going to see any alkenes, you're not going to see any ketones. Yeah.
Would we be expected to memorize how to point these out, or just expected to look at a reference and understand?
You should have a general idea of where they are and where you can find them. Okay? You should also know what the chemical tests are testing for and what the results are you should expect. Okay? All right, so there's the alkanes. All right, so now I'm going to show you two different alkanes. They're both 6 carbon, and I'm going to show you how the fingerprint region comes into play. Okay, so here's 2-methylpentane. That's a 6 carbon compound. It's an alkane, so there's just CNH, so we just have sp3CH stretching, CH bending, and then we have the fingerprint region. Hexane, same thing, 6 carbons, sp3CH, we've got our CH bending and our fingerprint region. The only way you can tell these two apart is by their fingerprint region. And so that's what you're going to be using to figure out your unknowns once you go to look things up. The fingerprint region of your IR spectrum should match the fingerprint region of what you say the unknown is, okay? Now, relative intensity of peaks can change with how much sample you have, but what they look like and what their relative intensities are and where those peaks fall, what wave numbers they're at, should be the same in the fingerprint region. So that's what you're going to use the fingerprint region for. You're not going to identify any specific functional groups for the peaks in the region, but you're using that to match up your information with what you say the known is. Okay? Does everyone see that? Okay. So make sure your fingerprint regions match. Okay? Now, when you are reporting IR data, you're going to use this table. This table's on page 520 in your lab manual. You want to always make sure that you use this table, okay? So we've put the table in the lab manual set up so that you use this table to report your IR information. So you give the frequency or the wave numbers of your peaks. What is the literature frequency for those same peaks? What is the intensity and shape? So meaning like a medium sharp peak would be, it comes down part of the way and is sharp, versus if you had something like an OH peak, you would say strong and broad, okay? So that's what this shape is giving you. And then what bond or vibration does it correspond to? So at 3078, we've got a CH stretch. This is sp2 CH bond. In the 29 to 28, late 2800s, we've got sp3 CH stretches. So that is what all this is corresponding to. So this is basically between the bond and vibration, and what comment you put there, you're telling what those peaks correspond to, okay? And what bond vibration they're corresponding to. All right, everyone good with this? And again, it's in your lab manual, page 520. Okay? All right, for this experiment, we're going to do something we haven't done before. In addition to a conclusion you're going to write, you have report sheets that you're going to fill out. These are at the end of experiment 6 for you, okay? So you're going to fill out all this information about your unknown and what is the name of the unknown. You'll list the physical properties. You'll give possible compounds you considered. So what are those plus or minus 10 degrees from your melting point and boiling point? What are they and what is their boiling point? Or melting point. Give the flame test information. Was it positive or negative? What kind of flame did you get? Give the results of your solubility test. You could use that table as an example, draw the table, and then put some comments about solubility. One note as far as sulfuric acid that I forgot to mention, if it reacts with sulfuric acid, then you count that as a positive solubility test, okay? So if it changes color with the sulfuric acid, then you count that as a positive solubility test. Okay, there's 2 pages to it, so don't forget the back side, okay? Then you're going to list all of your chemical characterization tests, and you want to give what were the observations and then what do those results mean. Okay, so you don't want to give just the chemical test, was it positive or negative. Give the chemical test. So for example, 2,4-DNP, 2,4-DNP, yellow-orange precipitate formed. That means positive for a ketone, okay? So you want to make sure you give the test, give the observation, give what it means. Then here's the IR table you're going to use. This is exactly like the IR table on page 520. Okay, so we've just given you that table to fill out, and then you're going to add a separate page of conclusions, and you'll attach your known IR spectrum and the literature IR spectrum for what you say your compound is. Okay, and with IR, don't forget table and also label the peaks on the spectra as well. Okay. Questions? No. Yeah. Like, what website did you use? List the website. So like if you use Sigma Aldrich or you use ChemFinder, those are probably the two best ones. Write what that website is.